Hey everybody, Mr. Piercy here, and today what we're going to be talking about are triangle sum properties. Uh, Coming into high school geometry, most students have a pretty good understanding of certain things about triangles already, meaning that they understand that the sum of the interior angles is going to be 180 degrees, and that how certain things are how we classify triangles by their sides and angles, whether it's acute, obtuse, right, scalene, isosceles, or equilateral. So here we have just some basic definitions. Triangle is a polygon with three sides. Interior angles, we do have to specify sometimes whether we're referring to an interior angle or an exterior angle, and you can see in the diagram that's been provided how the exterior angles are kind of produced. You can see kind of going around that the exterior angles are all kind of pointing in the same direction. In this case, they all look like they're being formed clockwise in relation to the sides of their triangle. So the new one that we have here is a corollary. A corollary is simply it's kind of an extension. It's just a statement that's easily proven using a theorem that it's talking about. So here we're going to talk about how we classify triangles. And again, in my experience, pretty much any student coming into high school geometry, based on their prior experience, is able to identify how we classify triangles by sides and angles. So scalene triangles have no sides that are the same. Isosceles triangles have at least two sides that are the same, and equilateral triangles have three sides the same. Now it's worth mentioning that equilateral triangles are also considered isosceles because they do have at least two angles or two sides that are the same. It's kind of like the idea that uh, all squares are also rectangles, so all equilateral triangles are also isosceles. Now here, based on the angles, if all three angles are less than 90, we call it acute. If there is one right angle, we call it right. One obtuse angle, the triangle is obtuse. Now, an equiangular triangle is the same thing as an equilateral triangle. Those are what we would refer to as, in geometry, as a regular polygon. A regular polygon is when all sides and all angles, all interior angles, are congruent to each other. So if a figure is equilateral, then it must also be equiangular. Now here, this is just an exercise of how you classify things. A shuffleboard, as far as I know, I've never played it. It always seems like one of those games that old people play when they go on cruises. I have no idea what the rules are, but according to the diagram, we can tell that the triangle that we're looking at that makes up the shuffleboard uh, scoring area, I guess, I don't know what it is, we can see that it is isosceles. So classify it by its sides and its angles. Well, this is not something that I generally like to do, but this diagram wasn't really drawn in any kind of better way, and the question wasn't written in a way that I really would like to have asked it, but it does kind of hit the point. If you had to classify the triangle by its sides and its angles, well, based on the congruency markings, we would say that the sides, there's two sides that are the same, so it must be isosceles, and the angle measures do all appear to be less than 90 degrees, so we would say it is also an acute triangle. So these angle measurements, I want to be clear, the 72, 72, and 36, those are just approximations that we're giving to work with the particular triangle. So when you're ready, here in the diagram or problem number one, I should say, draw a picture of an isosceles right triangle and obtuse scalene triangle. And when you have yours, come back and kind of compare them to mine because there are some things that we want to make sure that certain triangles have. So go ahead and stop now and come back when you're ready. Okay, so let's compare your triangles to mine. Well, in my diagrams, there we go. In my diagram, I do have an isosceles right triangle. Now, I know it's isosceles because I've marked two sides congruent, and I know it's right because I've marked that it has a right angle. So if you didn't include the hash marks showing that two sides are the same, or enough information to be able to claim that it is a right triangle, you can't simply say, well, it's a right triangle because it looks like it has a right angle. Now the obtuse scalene triangle, that one is fairly self-evident. There is clearly an obtuse angle, and I did my best to make sure that the sides were all clearly different lengths. Now here, coming back to what we were practicing with the distance formula, here, this is a very popular style of question that we like to be able to ask students in high school geometry. And let me be clear on what the expectations are. If I give you coordinates and ask you to classify the triangle based on its sides, you must use the distance formula to tell me what the lengths of the sides are. Now you can graph them to see do you have any excuse me. You can graph them to see do you have any horizontal or vertical lines, because you can just count those. But anything that's not horizontal or vertical, if you're trying to tell me how long it is and then classify anything based on its length, you must show me where the length is by using the distance formula. Consequently, what it's also asking you to do is saying, do we have a right triangle? Now, if we have a right triangle, we have to be able to justify that we have perpendicular lines based on the fact that slopes are opposite reciprocals. So also, if I ask you to justify, is this a right triangle or not, you must be able to say, yes it is, or no it is not, because I calculated these slopes using the slope formula, and they were either opposite reciprocals or they weren't. So here we have this triangle RST. Now, realistically, if I graphed triangle RST, the only thing I'm really going to be looking for to see, well, maybe it's isosceles. Maybe RT and RS are the same. They do kind of look about the same length, so I would do the distance formula on those first. So looking at RT, I would plug the values into the distance formula, and I would say, well, that's the square root of 52 units long. Looking at RS, I would plug in the distance formula here, and I would say, well, that's the square root of 65 units long. So those are definitely not the same. Now, just for the sake of doing it, they are having us go ahead and find the length of our ST, and we clearly see that that one is a much smaller length than the other two sides. So it's definitely not isosceles. This would be classified as a scalene triangle. And if you're not giving me the math using the distance formula to justify that statement, you won't be receiving full credit for the kinds of questions that I ask you with this. The only time you can give me an answer for a length to say it is this or it is not this is if the lengths are, or if the segments are horizontal or vertical, because you could just count those. Now again, looking at the sketch, and a lot of times the sketch is not provided for you. You might just want to sketch it out yourself, a little graph, to see what it might look like. Looking at the sketch, the lines that appear perpendicular to each other are going to be RT and ST. So those are the ones that I really want to be able to do the slope on. So I'm going to find the slope of RT, and I get a slope of negative 2/3. Then I'm going to do slope of ST. And when I do that one, I get a slope of positive 3/2. Well, those are opposite reciprocals. So that means the product of them is going to be -1. Now, because the slopes are opposite reciprocals, that's what allows me to justify saying, yes, this is a right triangle. So keep in mind on your homework assignments, on a quiz, on a test, if you try to say classification based on sides, you have to use the distance formula to show me why you're saying that. Same thing with the slope. If you don't show me that you found the slope to show that these are or are not opposite reciprocals, I will not accept an answer saying that it's a right angle, therefore a right triangle, unless, again, of course, it's a horizontal and a vertical line forming a right angle. So yes, we can say that this is a right scalene triangle. So moving on, here, this is where we've seen ideas as far as the triangle sum theorem. This is one of the things that pretty much every student coming into high school geometry on the first day could tell me about something they know about a triangle. That the sum of the three interior angles has to add up to be 180 degrees. Now the next one is something that's pretty new. This is the exterior angle theorem. What that's saying is that the measure of an exterior angle is equal to the sum of the two remote interior angles. Well, let's figure out, well, why is that the case? Well, if you accept the idea that the sum of the interior angles all have to add up to be 180 degrees, then what we can say is that, well, angle A and angle B must be supplementary to the interior angle ACB. So if angle A and angle B are supplementary to angle ACB, and at the same time, angle ACB is supplementary to angle 1, then you can conclude, and that I know I don't have the greatest handwriting, but even for me that was a bad word. All right, so then angle A, angle A plus angle B, I can't spell for anything today, must be equal to angle 1. That's the only way it's possible. Because angle 1 is supplementary to angle ACB, and so is angle A and B. They're supplementary to the same angle at the same time. Therefore, they must be congruent to each other. They must be equal to each other. So that's where that theorem comes from. And we could test it. We could construct some triangles and measure it, but we're just using some deductive reasoning to make that claim. So here we have an example of it. We have an exterior angle, BCD, and we have interior angles at point A and point B. Well, based on the exterior angles theorem, the measure of the exterior angle must be equal to the sum of the two remote interior angles. So the way that we would write it out geometrically is I would simply say, angle BCD must be equal to angle A plus angle B. So that's how we write it out geometrically. And now in step 1, we can see that we're just kind of substituting the values for angle A and angle B into the respective positions, and simplifying the equation to show that x is going to equal 41. Now the question is not asking us to find what is x, it is asking us what is the measurement of angle DCB. So we are going to substitute that back into the problem and show that angle DCB is 114 degrees. So here a corollary. Now remember, a corollary is just a statement that's easily proven using a theorem that it's talking about. Here, the triangle sum theorem says that the measurements of the three interior angles have to have a sum of 180 degrees. Well, if all three angles have to have a sum of 180 degrees, in a right triangle, half of that is at one angle. So if that one angle is 90 degrees, then the other two angles must also add up to be 90 degrees. And what they're saying is that, well, if the two acute angles of a right triangle, if they had it to be 90, well, we call those complementary, obviously. So that's what the corollary is saying. And that's really what this angle, or what this example, is asking you to take a look at. Here it's kind of giving you a situation where you have a ramp that's being built. A lot of times in algebra class you would see an application question like this based on the slope. But here we're kind of looking at the fact that we are making a right triangle and that the two acute angles of the right triangle must be complementary. So looking at the sketch that we have here, we can see that one angle is 8x and the other angle is x. So saying that 8x plus x, we'll say it's equal to 90. And then when we solve for x, we get x to be 10. So the measures of the two acute angles are going to be 10 degrees and 80 degrees, respectively. Now here, question number 2, this is my favorite kind of question. As a math teacher, this is the one where you have to show me, using the distance formula, are the sides the same or not? And if we look at the slopes to tell if we have a right triangle or not, because we have perpendicular lines. So I'm not sure why they gave us such a small amount of space to write it out, but what I want you guys to do is, looking at the last three problems that we did, go ahead and pause the video and answer these three questions on your own, and when you're done, come back and check to see how you did. Okay, so looking at example number 2, we have triangle JKL and the vertices J, or, -2, -1, and so on. So the first thing I wanted to do is I want to know, what does it look like? I don't have any horizontal or vertical lines, so that means if I want to do the distance formula, or if I want to know how long something is, I have to do the distance formula. Now looking at it, it looks like JK and LK might be the same length. So those are probably going to be the ones I'm going to do the distance formula on first, and that's what I did here. So looking at the distance formula, we can see that JK is 5 and that KL is 5. So it's not really possible for me to, I mean, it is possible to have, an equilateral triangle where all three sides are 5, but odds are the third side is not going to work out that way, and it didn't. When I found the length of the third side, JL, it worked out to be 5 radical 2. So now what about the slope? So again, looking at the sketch, which isn't required that you do, but I thought it was helpful, I found the slope of segment JK and segment KL because that's where I thought I was most likely going to have parallel lines. I'm sorry, not parallel, but perpendicular lines. And so the text that I have in red, that's the slope of JK, and this text that I have in blue, that's the slope of KL. And we do see that I do have slopes that are opposite reciprocals to each other. So that will allow me to say that I have a right triangle because right angles are formed with perpendicular lines. So now I can conclude that the triangle must be a right isosceles triangle, and I have the math that justifies that statement. So now moving on to question number 3. The measure of the exterior angle is again equal to the sum of the two remote interior angles. So angle BCD is going to equal whatever A plus B must give you. So when we set up our equation, we get this. 3x plus 16 is equal to 2x plus 52. Solving for x, we get 36. And that's all it's asking us to do. Well, actually, no, it's asking us to find the measurement of angle 1. And I really don't remember if oh yeah, I did. So the measurement of angle 1 is 72 degrees when we substitute it back into the problem. And finally, going back to example 4, what is the measurement of an obtuse angle formed between the ramp and the segment? Well, the acute angle that we saw between the ramp and the horizontal leg, well, that was a 10-degree angle. So that means that the other angle has to be 170 degrees because, the interior angle and the exterior angle of the triangle, they have to be supplementary to each other. So that's the angle. That's what I use to make my thing here. But that's pretty much it for this lesson, ladies and gentlemen. We're going to be talking again. All we're doing was talking about interior angles of triangles, exterior angles of triangles, and obviously how triangles are classified by their sides and their angles. But clearly we're going into more depth to it here than you might have done in previous math classes because we're including the use of the distance formula, we're including the use of slope, and obviously algebraic expressions for the angle measurements. So thanks for watching, guys. Any questions that you had, please make sure you share them with me, and we'll be seeing you guys soon. So take care, and thanks for watching.